Hello guys, and welcome to a new video, the second video of Calculus 3, where we're going to look at reducible first-order differential equations. So, first of all, what are reducible first-order differential equations? So, you can use a substitution of a third parameter, usually z or u or v if you're talking about velocity, to solve a differential first order equation into a form that you can solve either by using separation of variables or the integrating factor, which you should have looked at last video. If you have not looked at the last video, please get off this video, go to the first order differential equations, learn that, then come back here. Because you cannot do reducible first order differential equations without doing first order differential equations. It is that simple. So leave the video, come back, and then join us once more. Okay, so for those of you that know how to do first order differential equations, let's do this. So, the question, the example says, this is part A, so show that the substitution y equals xz. I'm going to write my z's on a cross just to make it easier because my 2's look like z's. Transforms the differential equation dy by dx is equal to x cubed plus 3y squared over 2xy, and this transforms into the differential equation of x dz by dx equals 1 plus z squared over 2z. Okay? So using this substitution of a third parameter z, we're transforming this original differential equation into a new differential equation where we can solve. The reason we do this is because we cannot solve this using separating the variables or an integration factor. So we're making it easier for ourselves to use a substitution and then substitute it back in to find the differential equation, to find the general solution of y. Okay, so we'll find a general solution later on. So given that y equals xz, we're going to differentiate that immediately. So we're going to say that dy by dx is equal to, using product rule, z plus x dz by dx. Okay, those are the only two that we need. So these are substitutions. Okay. So now we're going to substitute these into the first original differential equation. So we're going to say that z plus x dz by dx is equal to x cubed plus 3xz squared divided by 2xz. Okay, so simplifying that further, we're going to say that xz plus xdz over dx is equal to x cubed plus 3x squared plus this is a squared right here. Makes things a lot easier now. I did make a major mistake on the last video, which kind of ruined it, but still. 2x squared over z. Okay. So now what we're going to do, we're going to factorize that. So we're going to say that x, we're going to move the z over, so we're going to say x dz by dx is, we're going to keep the z there, sorry. So we're going to say that z plus x dz by dx is equal to x squared factorized 1 plus 3z. squared, which cancels the x squareds out. So we're going to 2x squared z. So they cancel. So now we have ended up with the result, nearly the result that we need. So we're going to say that x dz by dx is equal to 1 plus 3z squared over 2z, which is so damn close to the result that we need. So minus z, of course. So now what we're going to say is that crisscross smiley face, whatnot, dz, x dz by dx is equal to 1 plus 3z squared minus 2z squared all over 2z. Sorry about the coughing. And guess what? Is equal to the second. Is equal to the second, to the transformed differential equation, believe it or not. 1 plus z squared over 2z. Okay? Oh, sorry. I forgot one. It is usually they're worth about 4 marks. There are a lot of steps to follow, and you have to be so careful with what you're doing, especially with the algebra. If you get your substitutions wrong, you are screwed. You are not able... You're going to get nothing. Well, actually, you might get a few marks here and there as follow-through marks. But you're never going to get anything above 3 or 4 marks if you get your substitutions wrong. Otherwise, you'll get the follow-through marks. Oh, he's used separating the variables. He's used this, used that, used what? You know, the general stuff. Okay, so part B says find the general solution. I'm going to write it really down here because I don't need much space at all. You can kind of figure out yourself. So what it says here is that hence find the general solution to the original equation dy by dx equals x squared plus 3y squared all over 2xy, giving y squared in terms of x. Okay, so y squared, so using that substitution, y squared is equal to x squared z squared, okay? Sorry about that mess there. So once we've, thingied it and whatnot, we can say that z squared is equal to, actually I don't know if you can see that, let me move this back. So z squared is equal to, just trying to think now, y over x all squared, okay? So we get down to the equation. So using separating the variables and tidying things up and whatnot, the general solution is given by 1 plus z squared equals ax, where a is a constant, where a is an arbitrary constant. So substituting that in, y squared over x squared, whatnot, blah, 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 blah. Then y squared is just simply x squared, just rearranging everything. So, on top, x squared, ax minus 1. It's simple as that. And that is, in green pen, the general solution. Okay? It's a lot easier than you think once you've got your head around it. Once you've got your head around it, you're like, boom, algebra. I can use this substitution to substitute in this. So substitute, y dy by dx, substitute it in, get into this format, and then find the general solution or particular solution of given one. A lot of the time, I do apologise if I keep talking, but it's important this. Usually, a lot of the time, they'll tell you. A lot of the time, they'll tell you transform this original equation, into another differential equation which you can solve. However, you have to be aware you cannot rely too much on being given a new substitution, because some questions will ask you, using this substitution, straight to the cut, find the general solution of the original differential equation by using substitution. You don't know what you have to transform it into. You just have to transform it into something that you can solve using either separating the variables or an integrating factor. Otherwise, you are screwed. Don't rely on that too much. Otherwise, you're just going to get yourself into a massive habituating mess. Okay? So, we're just going to move on to another example, which we are we going to do that? Haha, yes, excellent. So this is what I mean. So, you using the substitution. So another example. So using the substitution, z equals y to the power of -1 to transform the differential equation dy by dx plus xy equals xy squared into a differential equation in terms of z and x. So we're getting rid of our y's in this differential equation and only in terms of z and x. Okay, so what we're going to do is... Oh, and what does it say? Solve the new equation. Oh yeah. Once you found your new transformed equation, then you have to give it in terms of z and then find a general solution. I'll just follow through and you'll see what I mean. Okay, so first off, what we're going to do, I forgot to put z's in. So z is equal to 1 over y. So we can immediately change that 1 over y. Y is equal to 1 over z. So when we differentiate 1 over z, so dy by dx is equal to minus 1 over, using product rule. Implicit differentiation. So dy by dx is equal to minus 1 over z squared dz over dx. Okay? That's what we're going to do. So now we substitute it into this equation. So now we get 1 over z squared dz by dx plus x, what's y? 1 over y. 1 over z, yeah, equals x 1 over z squared. Just doesn't sound all squared. Let's do that. That makes things easier. Okay, so how we're going to do, just going to tidy things up slightly. So I'm going to say that minus 1 over z squared dz by dx is equal to, oh dude, sorry about that. So what we're going to do is this plus x over z is equal to x over z squared. And now literally all we're going to do is times, so we're going to times everything by minus z squared, okay? So we end up with dz by dx, minus, don't forget, xz is equal to minus x, okay? That is our transformed equation. So I'm going to mark in red, this is transformed. So when I mean it's transformed. This is in the format of where we can differentiate. We can use the integrating factor. So you have to put it in something where you know that you can use separating the variables or an integrating factor. If you can't do that, if you can't if you can't get into your head that you can't transform it, then there's no point clicking onto this video then. Because if you can't get it, you can't use substitutions. I think you just have to look over it again. Just keep looking. Don't beat yourself over. If you can't follow what I follow, what I'm writing, then just click somewhere else. It's simple as that. Look at other people's methods. Don't just look at mine. Mine is quite different to, say, the textbook or something else, because I know how to do it. I've been taught how to do some of the methods. Okay, so now we're just going to carry on quickly, and then we'll get this video over and done with. So now we've got our transformed equation. Now what we're going to do, we're going to consider an integrating factor. Our integrating factor is, so IF is equal, so this was part A, sorry, this was part B. So the integrating factor is, whatever this is, in terms of Z. So, minus x, so e to the integration of, I'm going to factor the minus out, e dx, which is equal to e x squared over 2. And that's it, no constant, you don't need a constant for this. It's what I've been told. So, now you've got your integrating factor. Now you times it with everything. So, you will get e to the minus x squared over 2 minus x e to the power of x squared over 2 z. Oh, no, that's right. dz by dx, that, times e to the whatever, x e to the whatever times z, is equal to minus x e to the minus x squared over 2. It's so tedious, but you just, the job's got to be done, isn't it? Simple, it's just simple as that. Okay. Okay, so we have our integrating factor. So what's the next step? What we're going to do? The next step, ladies and gentlemen, is we're going to use reverse implicit product differentiation. So we're going to end up with d dx. This is your u, and x is your z is your v. So we're going to end up with z e times e to the power of x squared over 2 is equal to minus x e to the minus x squared over 2 dx. You're probably wondering why I put dx in Latin and why I put that so far away, because I'm going to integrate both sides. So that cancels, d dx, so differentiation of the integration cancels, so we end up with z e to the power of x squared over 2. Simple as that. So when we integrate that, usually we'd use by parts, which I think we do. But I'm just going to cut straight to the chase and... Oh, forgive me. It's a first guess, second guessed. So you don't have to use... I was looking at the example, I was thinking, do we use by parts or what do we do? First guess, second guess, believe it or not. I think. Because when you integrate that, you get... all you get is just e to the power of minus x squared over 2 plus c. That's all you get. I don't know what... You know what? If I'm being completely honest, I don't know why that integrates. Look on Symbolab or something like that. I do apologise for that, but... Okay, so... When... Okay, yeah, I know what to do from here. So, z is equal... So when we have to solve for z, part B says we solve for z. So that goes to 1. The e's cancel, and then you divide. So c e to the power of x squared over 2. It would be c divided by e to the power of minus x squared over 2, but we're bringing it up this time, so it's the reciprocal. It's just what we're doing. Okay, so now we have so this is the general solution of the transformed differential equation in terms of z. Now we got to consider our part c here, right here. We have our general solution for z. So, we now realise that y is equal to 1 over z. So, z is equal to 1 over y. Yes? So, we put it in there. So, we get 1. So, I get 1 over y is equal to 1 plus c e to the x squared over 2. So, now we flip it. So, we get y is equal to 1. 1 over 1 is just 1. Plus c e to the power of minus x squared over 2. So it makes essentially, oh sorry, didn't mean that. It's 1 over everything. 1 plus c e to the x squared over 2. That's it. It's fairly easy. Personally for me, I sound like a cocky prick, to be honest, but in all honesty I find this really easy, apart from maybe that integration there, but I hope you followed, because this, to somebody that has not ever seen this, it might sound a bit difficult, but it really isn't, trust me. Okay, so I'm just going to say some questions. So if you want to screenshot or pause the video, then by all means, because I don't really want my notes to fall out here. There we go. So if you want to try out some easier stuff, then go for it. Oh, let me put closer. So this is the easiest stuff. So this is probably grade C, grade D to maybe B, and then you get your A's right here and there. None of this is like A-star stuff. Unless you want to do that challenge question, then by all means. We're going to move on to second order differential equations, don't worry. We're going to do that soon-ish. So exercise 9A. Got to do this one more time. Okay, so if it doesn't go well, if nobody understands, then I might have to remake the video again, but with different questions, of course, and examples. But thank you very much for watching, and I hope this has helped in understanding reducible differential equations by means of a substitution. So next time in Calculus 3, we're going to be doing modelling first order differential equations, and then probably vector differential equations after that. I'm looking forward to it. So yeah, so I hope you have a good one and keep learning. So see you later, guys. Thank you for watching.